In Chapter 17, we'll be looking at conjugated pi systems and pericyclic reactions. The image that you are seeing is a picture of a shirt before with stains and one that went through the laundry where stains were removed. The stains were actually not removed, but instead they react with colored compounds to produce colorless compounds. So there's bleaching agents that can do this. The stain is still there, but it has been rendered invisible. If you illuminate the shirt with ultraviolet light, the invisible stain may be able to be seen again. So what we are seeing as color is a consequence of special conjugated pi systems. And in this chapter, we're going to look at structure, properties, and reactions of these conjugated pi systems. There's three different categories for dienes. The first that we will see is accumulated diene. And that is where the pi bonds are right next to each other. So the orbitals of those pi bonds, as you can see in this first orbital drawing here, this is for the accumulated, perpendicular to each other. So you can see these red lobes here and these other red lobes that are perpendicular. Two double bonds in a row make accumulated diene. If there's the one single bond in between, this is a conjugated diene. This is the representation of a conjugated diene orbital. So these pi bonds are separated by exactly one single bond, and the pi bonds overlap in the entire system, which is why we can draw resonance, because they have overlapping pi orbitals. In an isolated diene, it's separated by one or more single bonds in between there. The pi bonds are too far apart for them to have any extra overlap, so there's this gap here. Accumulated have the two double bonds in a row. Conjugated has the single bond in there where the pi bonds overlap. And the isolated has more than one single bond in between the double bonds, and the pi orbitals do not overlap. If you recall, this one here is an allyl double bond where there's a carbon coming off of there. We have a 1,3 diene. This is a 1,3,5 triene. In these two structures here, we have two single double bonds in between each of these double bonds. This is non-conjugated. We have two isolated alkenes. In this structure here, there's two single bonds. This is also non-conjugated. Heteroatoms can be involved in a conjugated system. We can see this conjugated enone here. So the double bond oxygen is part of the conjugated system as well. This one has one single bond. So it can be a CC double bond that's conjugated, or it can have an oxygen that is there as well. We can also see nitrogen as part of a conjugated system as well. In order to make a conjugated diene, if we have an allylic halogen, we can use tert butoxide to do an elimination to give us the least substituted alkene, to give us this conjugated diene, or you can use T-butoxide with a dihalide. So you want to use the sterically hindered base to make the diene. Conjugated double bonds are more stable than isolated double bonds because it's resonance stabilized. 1,3-butadiene is a common diene, has free rotation around the C2-C3 bond, which gives it two different conformers. In this conformer here, this is called the S-cis. If we look at this single bond, the alkenes are on the same side of that single bond. That makes it S-cis. If we look at this single bond here, the alkenes are on opposite sides. This is S-trans. And we look at the molecular orbitals of these. This is S-cis. And you can see the shape there. This one is S-trans. If we were to try to turn this bond up 90 degrees, this is not favored because this conjugation is disrupted. These conformations can rapidly interconvert to each other, and the p orbitals have effective overlap to give a continuous conjugated pi system. So in the s-cis we have overlap there, and in the s-trans we have overlap here. We can look at the energy of that. This is the potential energy for the s-cis. In order to go to the s-trans, it overcomes a large energy barrier, or activation energy, to get to the trans, which is lower in energy. This is higher in energy because of sterics. In these, the alkene electron density is away from each other, so this is more stable. So here we have a 1,3 diene that is trans-trans, or E-E. This one is cis-cis, or Z-Z. This one is cis-trans, or Z-E. So in these conformations down here, this is S-trans. So those are on opposite sides. Now it's on the same, so this is S-cis. This again is S-trans. And it can go through a different conformation and go to the S-cis. So this naming is a little bit different than the naming down here. The stereochemistry up here is a little bit different than this. This is referring to the diene with the S-trans. This is the technical if you were naming it EE, ZZ, etc. If we look at the resonance structures of these, some resonance contributors are more important than other ones. This first one here is the most important structure. We could draw a resonance structure where these electrons go into here, those come on to the end. That gives us this one, or you can move these electrons into here to get this resonance structure here. So we see some pi bonding character between carbon 2 and carbon 3, but we have the separation of charge, which is not ideal in resonance structures. If you have a conjugated diene with an extra p orbital here, there's also different resonance forms as well. So you can draw lots of resonance structures for conjugated systems. A good exercise here is to look at how we can move the arrows to get each of these different resonance structures. So that would be for this one here. So you can work through these and try to jog your memory on how to do resonance structures. If we look at the molecular orbital theory of butadiene versus ethylene, this is this molecular orbital of ethylene. There's a pi bond, and one electron is coming from each p orbital, and we have this low energy here. In butadiene, there's 4 different levels of the molecular orbital theory. We have 2 pi bonds, so we're going to have 2 pairs of electrons here. They have the lowest occupied molecular orbital. All of the orbitals are together. So we have all the blue on top, all the red on bottom. Then we have a situation where there's 1 node, 2 carbons in the blue, and then 2 carbons in the red. And then we have a 2-node system where it's alternating, and then the 3 nodes. So these are the empty orbitals, or unoccupied. And these are the occupied orbitals. So there's 4 different overlapping p orbitals, and it combines together mathematically to produce 4 molecular orbitals. So this one has no nodes. So that's no gaps in between there. So this is a different drawing of that. This is the no node system. We have 1 node, 2 node, 3 nodes. So this is the every other. In the no-node system, there's double bond character because the phases at C2 and C3 overlap. So this is a constructive overlap. In this one, we don't have double bond character between C2 and C3 because there's not overlap here. So it goes from blue to red. So there's no overlap. This overlaps because it's all blue on top. If we look at the orbital theory for hexatriene, it gets a little bit more complicated. So this is what you see here, the same 1 node where there's 3 red on top, 3 blue on top, and then we alternate the blue, red, blue, or red, blue, red, and then we have the gaps in between here all the way up to 5 nodes. So if we look at this and think about the HOMO and the LUMO, the HOMO contains the highest energy pi electrons, which are most readily available to participate in a reaction. So this is the HOMO, which stands for highest occupied molecular orbital. So these are the ones that can participate in reactions or are ready to do so. The LUMO is the lowest unoccupied molecular orbital. Because it is unoccupied or empty, it can accept electron density. If the compound is exposed to light, which it is here, so there's light right there, one of these electrons is excited and it can get promoted. The location of the HOMO has switched to the psi-4, and the LUMO has switched to psi-5. So the conjugated systems can react with light, they can absorb that photon, and then get excited, which changes the identity of where the HOMO and the LUMO are. So when this happens, these can perform photochemical reactions. So what you've seen previously with electrophilic addition with HX in an alkene, we have a proton transfer, which puts the proton on the carbon with more protons. The carbocation goes to the most stable carbon. The Br- does a nucleophilic attack on the carbon, and we get a halogen. With the conjugated diene as the substrate, we can actually observe 2 products. In the first one, the Br adds as it would normally as if this alkene wasn't there. In the second one, the alkene shifts and the Br is added to the other end. So to look at a mechanism of this, the arrows start the same. So the H adds, we get a proton transfer to add the hydrogen to the carbon with more hydrogens. Carbocation goes to the secondary. The Br- can then do a nucleophilic attack on that, and we get Br and H. This is called the 1,2 adduct, where this is 1, 2, 3, 4. So that is one product that you can get. So this carbocation here is in resonance with this. So this electron moves there. So we have that alkene, this hydrogen is still here. My carbocation is now on the end. And this, you might be thinking that it's primary. This is not going to happen because it's not stable, but you want to remember it is an allylic carbocation because it's next to that double bond. So we still have Br-, and that's going to attack where the carbocation is. And we get a Br on the end. This is the 1,4 adduct, where this is 1, 2, 3, 4. So we get a mixture of products due to the resonance. If you're adding Br across the double bond, if you add Br2 across the conjugated diene, we will see something similar. We'll have a 1,2 adduct and also the 1,4. And notice that double bond has shifted in between there again. If you have this alkene here, if you have this diene, you can get this 1,2. We can get the 1,4. We can get the 1,2 that would have added in the opposite direction. And if we do the 1,4, it would be the same as this one. So this is a 1,2. This is the 1,2 in the other direction. This is 1,2. This is 1,2. And this is 1, 2, 3, 4. And if we number it the other way, this would be 1, 2, 3, 4. So our products would be the same here. So if you have an asymmetric conjugated diene, you will have a mixture of products. We can control which product is preferred using thermodynamic versus kinetic control. So you're familiar now with this product. If you have the conjugated diene, we add HBr, we get a 1,2 product versus a 1,4. If you do this reaction at different temperatures, we're going to see different products. Running this temperature at 0 degrees Celsius or cold, we get 71% yield of the 1,2 product and 29% yield of the 1,4 adduct. At 40 degrees, which is considered warm, it's slightly warmer than body temperature. This is 15% and this is 85%. A cold temperature prefers the 1,2 adduct, which is the less substituted alkene. The warm temperatures prefer the more substituted alkene. So we can use temperature to control which product is preferred. If we look at the potential energy diagrams, once the reaction gets started, it has to overcome an activation energy to do the proton transfer. We then form the carbocation. For the Br- to attack here, this does not take much energy because it's going to make a less stable product. So the activation energy hump is smaller. So this can find this pretty easily. It takes a little bit longer and more energy in order to form the more stable one. So that's why it happens at higher temperature. So the higher temperature gives it the extra energy to do the nucleophilic attack and the resonance electron shifting to form the more stable adduct. So the 1,2 can form relatively quickly because the carbocation is right there. For the 1,4 adduct to form the more stable alkene, if you want the more stable product, it needs more energy, which is provided by that heat. So we add that heat to the energy to give it the bump to go over the higher activation energy to get the nucleophile to attack to give us the more stable alkene. So the 1,2 product is favored at low temps because of proximity also, and it doesn't have enough energy to convert the allylic carbocation. So kinetic products give us our cold temps, and the reaction happens quickly. The thermodynamic product is a warm temps. It needs more energy to convert it to the allylic carbocation, and it also is slower to give it more time to do that. So we're going to predict the products for the following reactions here. So cold is the one that gives us the less stable alkene, or the 1,2. So we'll get this one. We can also get the 1,2 in the opposite direction. That would be the 1,2 in the other direction, where this is 1, 2. In the warm conditions, we're going to get the double bond forms here. We get the 1,4 addition. And we can get one for in the other direction as well. So isoprene is a natural product that can undergo several polymerization reactions to form rubber, which is cis-1,4-polyisoprene. And you can kind of see these units that are repeating here. So rubber is made in the lab from polymerizing isoprene, and we can use this for several different things. And we can change the branching to make different levels of rubber. Chloropropene is also used in polymerization. You can see those units there. This is used in neoprene, which can be used for installation of electrical wiring, fan belts for automobiles, and scuba diving wetsuits. So these are polymerization reactions.